Okay, we'll go ahead and get started. Can the people on Zoom hear me and see the screen?
Yes.
Okay, thank you. So the first thing I want to start out with is there's going to be a slight change of schedule. And so we were going to start on chapter 12 today. We're going to do that. But then on Thursday, we were going to have a quiz. We are not going to have the quiz on Thursday. It'll be next Tuesday. And let me tell you the reason why. So, hold on a second here. So the reason why the quiz is not going to be this Thursday, it's going to be next Tuesday, is that Webster University is in the process of hiring another chemistry professor. And so they're doing the interviews for the candidates this week. And one of the things they asked the candidates to do is to give presentations at classes. And since one of the things this person is going to do is do some teaching in Gen Chem, the two classes that we have on Thursday, this one and the one after it, candidates are going to teach during that time. Once I get more information on who it is exactly and the Zoom link, I'll post that on Canvas. And so what I would ask you to do is on Thursday, for those of you who come to class, don't come to class, just dial in and you'll be given an opportunity to give feedback on the presentation and the candidate. So this is your opportunity to help the department choose the best candidate. So I don't know what they're going to talk about. It's not going to be chapter 12, or it could be. It's kind of up to the candidates. And you're not going to be tested on that or anything, at least what they present. So it may be something that we had last semester. It may be something that we will do this semester. I really don't know. They gave the candidates a lot of latitude in that. So once I get the more details on it, I will let you know and I'll post it on Canvas, and that'll have the Zoom information for you to be able to dial in, and it should have a form for you to provide feedback and then who to give the feedback to and all that. So it's kind of exciting. A new faculty member will be here in the fall, and it's your opportunity to participate in the selection of that person. So any questions about that? Okay, so once again, no quiz this Thursday. It'll be next Tuesday. And then I've also on Canvas posted an updated lecture schedule. So things, as you can imagine, kind of shifted a little bit from here on out. And so that's posted as well. So you can see kind of the new tentative, I stress the word tentative because here we are in week 2 have already had a change. The tentative dates for what chapters we're covering, quizzes, exams, things like that. So I appreciate you being flexible on this and you know, spending some time evaluating these candidates, and we'll go from there. So thank you for that. Okay, let's see. So today what we're going to do is we're going to start talking about solids. And one thing I want to point out about the material we'll be covering is a lot of this has to do with something called crystal structure. And so that'll become a little more clear as we go through the material, what that means. But I wanted to just mention that up front a little bit more because one of the chemistry professors here, Professor Groneman, this is kind of his, this is his area of expertise, and this is what he does his research on, is crystal structures. And so as we go through the material, if you find it interesting, If you say, gosh, I'd like to learn more about that, I'd like to learn at a higher level than what we cover in this class, talk to Professor Groneman and see about doing some research in his group. Whether you're in biology or chemistry or whatever, I would also just in general strongly encourage you to start doing research as soon as possible. That's always something good because it helps you kind of get a little more experience than what you get just in the classroom. And it also helps you understand maybe what you like to do or don't like to do. I know for the science majors here at Webster, you're required to do a senior thesis, and a lot of people wait till their second semester of senior year to do that. And that's fine if you do that. That's fine if you do that and wait, but I'll tell you, the more research you can do, because sometimes you may pick someone and you do some research with them and you think, well, this isn't exactly what I'm interested in. Then you have an opportunity to move on to someone else and try something different. So anyway, if you find the crystal structure stuff interesting, talk to Professor Groneman. I'm sure he's pretty excited about this stuff, so I'm sure he'd be thrilled to talk to you about it. And then just once again, no quiz this Thursday. I'll send the Zoom information out about evaluating these faculty candidates, and then the quiz will be next week on Tuesday. All right, any questions about any of that stuff before we start the chapter? All right. So when we talk about solids, we classify them based on the type of interaction that the atoms or the molecules have amongst each other. And so one of the things is something called metallic solids. And so as you might imagine, that's where you have metal atoms involved. And in that case, the solids are held together, and the term they always use is a sea of electrons. So the electrons aren't with any particular atom. They're just kind of shared amongst the different atoms. And it's considered to be like a sea of electrons is the phrase you'll always hear. And so those valence electrons are kind of shared amongst the atoms. And that's what gives it some of its physical properties as well. So one of the physical properties, metals can conduct electricity. And that's because of this kind of sharing this of sea of electrons. Another thing is metals are pretty strong. So if you just think of the metals that you would come across, copper wire, for instance, is one I always think of. You know, it's pretty strong. You can bend it, you can twist it, all that kind of stuff. It's good at conducting electricity, so good at conducting electrons. And it's strong without being brittle. And when we say brittle, we mean if you bend it, it would snap. Okay, and so that's a couple traits that metal solids, metallic solids have. Ionic solids, and this is the ionic solids, a lot of times are the ones we think of when we think of solids and crystals and things like that. That's where you have cations and anions present, and they have mutual electrostatic attraction. It's that opposites attract that we talk about. And one that always comes into mind when you're talking about ionic solids is table salt, sodium chloride. So that's a good example of an ionic solid. They don't conduct electricity and they tend to be brittle. So you think about the table salts, especially if you have some bigger pieces of salt where it's pretty brittle. You can smash it and it'll break apart. That's that brittleness that we said the metal solids don't have. Another type of interaction centers around covalent network solids. And that's where you have atoms where there's a covalent bond associated with it. And it's a network of these covalent bonds. And remember, we talked about, when we talked about bonding, we said covalent bonds are really strong. And so as you can imagine, if you have a network of covalent bonds, that's a pretty strong material. And by strong, it means it's pretty hard to destroy it. And the classic example of this is diamonds. So diamonds, as we know, is just carbon, but it's the way the carbon is bonded to each other in this lattice matrix that gives it its strength. And, you know, usually when we think of diamonds, we think of, you know, jewelry and things like that. But the other thing about diamonds is it's really, really hard. It's often used in cutting tools and things like that because of how strong it is. The other area where you get these covalent network type solids are semiconductor materials. And semiconductor materials, that's the stuff that goes into computer related things, computer chips and stuff like that. And we'll talk about that a little bit later in the chapter about the semiconductors and how that kind of works. But the key to this is these really strong materials like this have this covalent network where you have actually those strong covalent bonds taking place. Molecular solids, this is when you have discrete molecules and they're held together by the weak forces that we talked about in last chapter. So that's the dispersion forces, the dipole-dipole interactions, the hydrogen bonding. And so because these forces aren't as strong, the result is the material tends to be a little softer. And associated with that is the melting points are lower. So the solids that we talked about in those first three types, those tend to have higher melting points than this last one, the molecular solids. Any questions on these four types of solids and the interactions that are associated with them? Okay. So here's a visual look at kind of what we mean when we talk about these different types of solids. And I'll say one thing about this chapter, and to be honest with you, you'll either love this chapter or you'll hate this chapter, because a lot of it is these kind of figures like we're going to see here. Me personally, I have a hard time visualizing this stuff. Professor Groneman eats and sleeps this stuff. So he loves this. This is not my favorite stuff, but it is very interesting. And so one thing I would say is spend some time looking at the pictures in your book, because that's going to be better than what I have on the slides or what I could draw or anything like that, because you really have to get into the mindset of visualizing how this stuff fits together to understand it. And if you're like me, you got to look at the pictures a few times to really kind of grasp what they're saying. And so when we look at the ones here, if we look at metallic solids, remember we said that's where you have that metallic bonding, that sea of electrons. And in these photos, in these pictures, each circle is a little hard to see on the screen here. It's a little bit better, but they'll have different colors for the different atoms. And then you have to look in there to subtlety to see how they fit together. And that's what each of these are showing. They're just showing how they fit together. We're going to get to some others, other pictures that showed a little bit better. So there are two other types of solids that we'll talk about a bit in this chapter. One is polymers. And so when you think of what is a polymer, basically polymer is plastics, okay? So different types of polymers give you different physical properties, but the common thing is they're all considered plastics. And what a polymer is, you have a long chain of atoms connected by covalent bonds, and sometimes the chains can be connected to each other through an intermolecular force, But what you get in polymers is you always have a unit, so a small molecule, and then it repeats itself. You also can have something called a copolymer, where it'd be two different units repeating themselves. And we'll talk about this later in the chapter. But the key thing with polymer is usually high molecular weight, so in other words, big compounds, and then repeating units of either one or two units, types of units. It says here that polymers are stronger, more flexible material. I would say that's sort of correct. Depending upon the type of polymer, some polymers are very strong, some are not so strong. Some are pretty flexible, some are pretty brittle. This is one of the tricks in polymer chemistry, is designing things that suit your purpose. One thing that you see in the news a lot these days is you see a lot of information about plastic waste, right? So you always show the pictures of the water bottles in the ocean and stuff like that. Well, one of the problems is that those polymers that are in the plastic bottles are strong. They don't break down very easily. And so in the field of polymer chemistry right now, there's a lot of effort going on to come up with polymers that are strong enough to do whatever their purpose is, but then don't stick around for 100 years or something like that. Because in a perfect world, you'd want that water bottle to maybe be good for maybe a year while it's sitting on the shelf and you're using it. And then after that, it decomposes into some harmless type of decomposition product. So polymers, there's a whole discipline called polymer chemistry where people study the different types of polymers. We'll talk about it just a little bit. The other one is nanomaterials. And the nanomaterials, those tend to be crystalline compounds, and the crystals are pretty small, 1 to 100 nanometers. And so because of the size being so small, they tend to have different properties than the bigger crystalline materials. And so we'll talk about some of the uses for those types of materials. When we talk about solids, we talk about something, we use the term organization of the solid. And what that means is, it's kind of like, what's the arrangement of the atoms or molecules within that solid? And solids that have a real regular repeating pattern of the atoms, so in other words, that have a lot of order, those are called crystalline. And crystalline solids with that ordered organization within it, that repeating pattern you'll see within it, those are studied quite a bit. When it's not ordered, it's called amorphous. And the amorphous ones are the ones that really have that lack of order in the arrangements of the atoms or the molecules, and they're a little less studied. Okay, so now we talked about these different types of solids and the interactions that are involved with them. And we started talking a little bit about order. And so now we're going to go through some ways that people define crystal structure, order, things like that. So these are terms that you're going to have to get comfortable with. You're going to have to basically memorize and understand what they mean, because they're pretty much definitions of how people talk about crystal structures and stuff like that. So the first one is the unit cell. And so in these ordered solid materials, you have a repeating pattern, and that's called the unit cell. And this is a certain arrangement of the atoms. You'll have that arrangement, and it'll repeat, 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 repeat. And that's that order or structure that the material has. So that crystalline solid is defined by the size and shape of the unit cell, and we'll go over what some of those are. And then also, once you have that unit cell defined, where are the atoms located within the unit cell? So we're talking about order in solid materials. We're calling that this repeating pattern is called a unit cell, because we said in those ordered crystals, we have things line up a certain way. And then that crystalline solid is defined by the size and shape of that unit cell, and also the locations within the atoms within the unit cell. So real important that you understand and think about what we're saying here. This is how that you can characterize these different solids, these crystalline solids, based on the shape of that, size and shape of that unit cell, and then where the atoms are located in there. So you'll have a geometric pattern of points on which the unit cells are arranged, and this is called the crystal lattice. All right, so once again, we have the unit cell, which tells us what that repeating pattern is. The structure of that crystalline solid will have a size and shape related to that unit cell, and it'll have location of atoms within the unit cell. And then finally, that geometric pattern of points on which the unit cells are arranged is called the crystal lattice. So you think of what a lattice is. A lattice is just a series of things, right? Like if you have like a lattice or a trellis or something that you have plants on, you think of what that looks like. Same idea here of what we're talking about with these crystal lattice type things on solid material. Okay, continuing on with our definitions, we have something called lattice points. So the positions that define the overall structure of the crystalline compound are called lattice points. And each lattice point has an identical environment. It has an identical environment because remember we said these are just all repeating things over and over and over. So each one is seeing the same thing. In a few moments, we'll have some slides with some pictures, and I think this will be a little more clear. Lattice vectors connect the points and define the unit cell. And remember, when we say something is a vector, it has both direction and magnitude. Okay, so if you've had physics, you probably remember that from physics defining vectors. So the next slide here, we're going to show some examples of this in 2 dimensions. Then we'll move on to 3 dimensions. And 3 dimension is really what you're talking about. But first we'll look at the 2 dimensions. So here's some 2-dimensional lattices. So if we just kind of start here on the left with the oblique lattice, so this kind of rectangle type shape. So in other words, the black lines, that's the lattice. And then we see within there the unit cells. So once again, the black repeating thing is the lattice, and then we have the unit cell is this kind of bluish one in there. You see with the 2 vectors in this, A and B, we've got a direction and we've got a distance. And then we have gamma here, which is the angle between those vectors. So what you see on each of these, you have the same thing. So here in this next one, we have the square lattice. The other thing I want to point out is it's telling us, for instance, with the oblique lattice, A and B are not equal, so one is bigger than the other. When we look at square lattice, as you might imagine, A and B are not equal because it's a square. The next one, rectangular lattice, we have A and B are not equal because it's a rectangle. And we see in the square lattice and the rectangular lattice, our angle between A and B is 90 degrees. And then finally, the last two, hexagonal, we see the hexagonal shapes. And then we see A and B are equal, but now that angle between them is 120 degrees. And finally, rhombic, we see that, and we see there's two separate. We have a centered rectangular lattice here, and then we have another shape here as well. So we move over to, see that where we see, once again, the lattice is the black lines, the framework, and then the colored stuff inside, that's what the unit cell looks like. So this is meant to be an explanation of what we talked about here with the lattice points. Any questions on this? Okay, so this is a two-dimensional lattice. So when I say two-dimensional, what I mean is it's just flat on the piece of paper. In a little bit, we'll get to three-dimensional lattice. So then we'll have a third dimension to be concerned about. And then, like I said before, it can get a little more confusing when you get to that. And here's an example of 3D lattices. So there's 7 basic ones, and that's what we have here. Before we look at those, let's take a look at this vectors over here on the far left. We see we have an A, a B, and now we have a C vector as well. That's that third dimension that we talked about. The other thing we have is we have, instead of one angle between A and B vectors, we now have 3 angles. We have an angle between B and C, an angle between A and C, and an angle between A and B. So we've got more to think about once we get to the third dimension. And that's really what's going on in these solids. Solids aren't two-dimensional, they are three-dimensional. And so when we look at the ones, these 7 choices that we have, the first one we have is cubic. And in that case, those 3 vectors are equal. And also we see that the 3 angles are equal. So as you might imagine with a cube, sides are all equal and the angles are all equal. In this case, 90 degrees. Tetragonal, we have A and B are equal, but they're not equal to C. So in other words, one side is longer than the other 2. The angles all stay the same, 90 degrees. Orthorhombic, we see that none of the vectors are equal, but we maintain that 90-degree angle between them. Rhombohedral, vectors are equal, but we see that the A and B angles are equal, but they're not equal. None of them are equal to 90 degrees. So it's kind of leaning over, so to speak. Hexagonal, A and B are equal, C is not, and we see here that we have A and B are 90 degrees, gamma is 120 degrees. then we have monoclinic and triclinic. Monoclinic, each vector is different. We have a couple angles at 90 and one that's not at 90. And then triclinic, once again, none of the vectors are equal. And in this case, none of the angles are equal. So when we talk about the lattice, crystal lattices, and we move into this three-dimensional type look, they're going to fit into one of these. Okay, these are our choices. So remember, we had 2D lattices here, where we said the lattice was the black framework, so to speak. And we had information about the magnitude of those vectors, A and B, and then the angle between them. And then in this one, we drew some colored shapes in there, which is the unit cell. Then we kind of expanded it to that third dimension. That's where we added the C vector. And so with that third vector, now we get something that we actually start having shape and start seeing some, some dimensionality to it. And so we had these 7 choices for this, and the difference is all centered around the magnitude of the vectors, A, B, and C. Are they equal? Are they not equal? Is it some combination? And then also those 3 angles that we now have to work with, alpha, beta, and gamma. So once again, this is something that you should know, okay? Any questions on the 2D or 3D lattices? Okay, so it gets a little bit more jumbled as we go through because there's something called primitive and centered lattices. So primitive lattices are ones that have atoms only at the lattice points. And so the lattice points, like if we look at this cubic lattice example, the lattice points would be the corners of this cube, okay? So going back to this one, in each of these, the lattice points are the dots. So in other words, it's the corners. So if this was a primitive lattice, we'd have atoms at the corners. There's something called centered lattices as well. And that's when you have atoms in another location, not just on the corners, okay? And so you kind of have 2 choices here. One is you can have points at the corners plus 1 right in the middle of the unit cell. That's called a body-centered cubic lattice. Below it, we see that if we had lattice points in this cubic setup at the corners, so in other words, at the lattice points, and then at the center of each face. So this is where you got to think about it being 3-dimensional. So you've got an atom at each of those corners. So that would be 4 up on top and 4 on the bottom. But then on each face of it, you would have another one. So you'd have 1, 2, 3, 4, 5, 6 more to go, right? 1 on the front face, back face, side face, other side face, top and bottom. So that would be a face-centered cubic lattice. And what you'll see in a little bit, because we're just looking at one portion of the lattice here, these are stacked upon each other's, and you start getting sharing of these. So like the corner one is shared with other things that attach onto there in this lattice makeup. Same with the side. The centered one, the body-centered one, that one atom that's in the middle there, that's not sharing anything with anybody because it's right in the middle. It's not on an edge. So once again, I would suggest that you spend some time looking at the diagrams because it really is a pretty visual thing that you need to get comfortable with. Okay, there's also something called a motif. And this is when the atoms, none of them are on the lattice points. So we just talked about all this stuff of lattice points and showing you where they're on there or things like that. Well, there's actually instances where nothing lies on the lattice point. So we see here over on the far left, we see the lattice points are the 4 dots in the corners, but our 2 atoms aren't on any of those corners. They're kind of at an angle there and they're in the middle. So what the heck does that mean? Well, this is what I was telling you. If you take 1 unit cell and look at it, it looks like we have on the left here. But really, when we're talking about this, we said the lattice is a series of these unit cells. And that's what we see in the second figure. So now we've got a bunch of unit cells, and we see those atoms within it, but there is structure to that. And then in this third figure, we see that if we have some interactions between these atoms from one unit cell to another, we start to see that we can have a connection there, some type of interaction, whether it be bonding or electrostatic or whatever. And then that looks like a repeating pattern there. We can see like a hexagonal shape all throughout there. And you get this interconnecting type of structure, even though none of the atoms are on one of the lattice points. And this is the kind of thing here that you might see with a diamond or something like that, okay? So just when we thought, oh, it's got to be on those lattice points, we see there are examples of where you can get structure even though you're not on a lattice point. So the big takeaway on all this stuff is we have these solids that form crystals, and they form crystals because they have some type of defined repeating structure. And we've got a lot of choices on what that structure can be, but they all have structure. If they don't have structure, we don't have the crystals. Okay, there is some homework associated with this. I would encourage you to take a look at it. I'm not going to go through any of it because I think it's getting comfortable with these 3D structures, 2D structures, things like that. So take a look at those. The answers are posted if you get stuck. And if you have a question, you can always send me a message and I'll be more than happy to answer. Okay, so if you recall, we started today talking about different types of these interactions. We had metallic, we had ionic, we had a couple others. So what I'd like to do now is go through and talk in a little more detail about the different types. And the first one we're going to do is metallics, the metallic structure. Remember, the metallic structure is that one that we said the metals have some positive charge to them. Then there's this sea of electrons that kind of mushes around them all. And that's kind of the idea behind these metallic structure type things. So those valence electrons, the official chemistry word is delocalized rather than smushing around. And so but it's throughout the solid. It's not linked up to any one atom, and that's the key. So the metals conform to one of the cubic unit cells: simple cubic, body-centered cubic, or face-centered cubic. Remember, we said that in the simple or primitive cubic, you have things on the lattice points, so in other words, on the corners. Body-centered, once again, you have the corners, and then you have an atom stuck in the middle. And then you have face-centered, where you have the corners, and then on each face. And down below, we see the structure here with the atoms in here. And so what you see is on the first one, the primitive, think of it as these 4 atoms stuck on top of each other. And inside here, you can see the cube, that cubic unit cell for the lattice type structure drawn in there, and you can see how that holds together. Body center, once again, you have 4 on top, 4 on bottom, and now we see 1 atom in the middle of that structure, and that's that body-centered atom for the body-centered cubic lattice. And then finally, and this is where it gets a little more jumbled to see, you've got 4 on top, 4 on bottom, and then you've got 1 on each face. And so that's where you have to really look closely in there to kind of see how they're fit together. The last thing I want to just point out is in the 4th diagram here, the one with the red ball in the middle. What it's and this is how we see that a corner, so one of these corner atoms is shared by 8 unit cells. And so where does the 8 come from? You've got 1, 2, 3, 4 on its plane that it's on, and you've got ones above and below. So the corner ones, and try and make sure that you can understand that. So that corner atom, only 1/8 of it goes to each unit cell, okay? And we'll see that the face ones, only half of it goes to that unit cell. Body center, the one in the middle of that, that's the whole thing is in that unit cell. So this goes back to that kind of stacking to it and how they fit together. And because it's that repeating pattern, you get some sharing as you define these lattice structures. Okay, so as I said, the corner ones in the unit cell, 1/8 of it is within that unit cell because it has this sharing amongst 8 different unit cells. The edge is 1/4. The face is 2, and anywhere else is 1. And we have a picture here that will be, I think, a little easier to see when we talk about this. So here, what we have is on the right-hand side of these pictures is we've taken that 3D structure that we had earlier, and then we've carved it up as if it was a unit cell. And that's where you can see on the top one, you can see the corners are carved up and only 1/8 of it is there. The body-centered one, we see 1/8 from the corners, each of the corners, and then we have 1 in the middle. And then finally, on the last one, we have the 6 faces, we have the 8 corners, and we see how those are carved up. Half an atom at the 6 faces, 1/8 of an atom at the 8 corners. So what that means is, if we go back and look at the totals for the primitive cubic metal, there's only 1 atom per unit cell. So even though we go back here and we see down at the bottom here, this picture of primitive cubic metal. Well, it looks like we've got 8 atoms there. But really, in terms of how much of the atom is there in that unit cell, it's only 1. Because of this, 1/8 of the corner is in each unit cell. And so the end result is 1/8, we have 8 corners, total of 1 atom per unit cell. For that body-centered, once again, we have 1/8 of 8, so that's 1 atom, and then that one in the middle is totally in there, it's not sharing anything. So then we have 1 atom there for a total of 2. And then finally, the last one we have with the faces, we have 1/8 of 8 for the corners again. Then we have half of 1, so half is in that unit cell, half is in the other one next to it. And we have 6 of those faces, so that's a total of 3, so we have a total of 4 atoms per unit cell there. Any questions on how we got how many atoms are in each unit cell for each of these configurations? So you need to remember this, that corners, 1/8, edge, 1/4, face, 1/2, and then anything else is 1. And relate that back to these structures. And then once again, looking at the sharing here, kind of the carved up version of these diagrams, I think are useful. And it allows you to see how you get to what's the total number of atoms in the unit cell for each of these configurations. So far we've been talking about unit cells, and we've talked about this lattice structure, and we just now showed a little bit of how you have that unit cell, but then as you start getting in the lattice environment, you're going to have sharing of those atoms. They're in more than one lattice and things like that. Well, all this is leading us up to how do the atoms in the overall crystal pack together? Okay, and so a lot of these like to pack as efficiently as possible. So it's almost like you're going on a trip and you're packing your clothes. How do you fit the stuff in so everything fits in and you can get the most stuff in? So in crystals, the atoms usually like to pack together as closely as they can. And there's 2 common types of this. One is something called cubic close packed, CCP, and the other is hexagonal close packed, HCP. And so what does that mean? So up here, we see side views of the 2 ones. And so you see A, B, A, B, and then here A, B, C, A. We'll talk in a moment what the A, B, and C mean, but we'll have a little better picture on the next slide. But just in general, it means the arrangement is the same for A, B is a different arrangement, C is a different arrangement. So for the hexagonal close packed, which is what we're talking about here, we see if we look at the unit cell, we've kind of got this angle thing. And when we look at cubic close packed, we've got a little different shape there. Let's go to the next slide. I think that illustrates it a little bit better. Okay, so we're talking about, we're going to stack these layers up. Let's do the hexagonal close packed first, the one on the left. If you look up at there, you see all these atoms, and we're looking down at it. Okay, so we're up over it, we're looking down. And I want to point out a couple things here. You see some of the spaces in between the atoms have a little red dot and some have a yellow dot. So what that's going to do is going to help us visualize how this next layer is going down on top of it. So now we're adding a second layer of atoms to it. And what do we see? We see that the atoms are added to that first layer so that the yellow dots are covered up. Okay? So we don't see the yellow dots anymore because those atoms, think of it as little balls, sit down right in the space there where the yellow was. We still see the red dots, right? We haven't covered those up because we set things down here in each of these yellow spots. So we still see the red. And now we have this kind of whitish gap. That's the gap in that second layer, okay? Let's put another layer on top. And now with this, we're going to set this next layer down so that it goes into the whitish gaps, and we still see the red, okay? So we've set it into the white, now we see the red still. And so that's why that is ABA. So we have the first layer was A, and it looked a certain way. We put B in, and it covered up, in this case, our yellow gaps, but it maintained the red. So by putting it into that, in this case, it's now kind of a whitish gap, put it into there again, we still maintain that red gap. And so that third layer is set up the exact same way that our first layer was. So that's considered the A layer. B was a little different because we had an offset there. And so what you see is that's the ABA. This is the side view that we're seeing, the ABA down at the bottom. So if it used to be that people would take styrofoam balls or something like that and make these and kind of set them on top of each other. I don't see that very often anymore. Let's look at cubic closed packed, CCP. So once again, we start off with the yellow gaps and the red gaps. We add the second layer and we've covered up the yellow gaps. So after adding this second layer, it's exactly the same as the first one that we did, right? We've covered up our yellow gaps, but we can see the red gaps. Okay, now it's going to be a little different. Now we're going to add something that puts an atom on top of each of those red gaps. And so now we don't see the red gaps anymore. We see these clear gaps, but we don't see the red, we don't see the yellow. By setting them down in that depression, that third layer that we added was different than either the A or B layer. And that's where we get this ABC configuration that we see down on the bottom here. And if you look closely, you can see with these vertical lines that are drawn on the slides, that it's a little bit different from the ABA and the ABC in terms of the arrangement of how those fit together. So this is the kind of stuff we're talking about when we're talking about crystal structures and just how things are aligned and stuff like that. It's almost like putting together a puzzle of how do things fit together most efficiently. And in these two cases for the metals, we have a couple of options here on how this packing goes. Any questions on how the atoms stack in the layers? Okay. Okay, so as we just saw, cubic close packing has an ABC stacking. Remember we said this is that ABC, and that will just repeat, ABC, AB for the other one, okay? We said the hexagonal close packing has AB stacking. In each case, each sphere has 12 equidistant neighbors, 12 in the same layer, 3 above and 3 below. So if you go back and look at all this a little more carefully and kind of twist it around so you see the different angles, what you'll see is that in each of these cases, each sphere, so each atom, has 12 equidistant nearest neighbors, 6 in that layer that it's in, 3 above and 3 below. The term that we use for this is coordination number. And coordination number is the number of atoms immediately surrounding a given atom in a crystal structure. Okay, so coordination number is the number of atoms that are right next to a particular atom. And the coordination number gives us some idea about packing and stacking and all that kind of stuff that we've been talking about. Okay, so let's talk about a little bit more about some different types of metals and how this packing stuff kind of fits into some metal properties in that. So how many of you ever heard of an alloy? Has anyone ever heard of a metal alloy? Okay, we've got some people here who have. So an alloy is a material that contains more than one element and it acts like a metal. And so alloys are really important because what you find is that straight metals by themselves often don't have the physical properties that you want for whatever it is you're using the metal. And so by having some combinations of things and making these alloys, you can get physical properties that are more appropriate for whatever you're using the metal for. Here are some common alloys. The ones I'll point out are, one is bronze. You hear about bronze? Well, bronze is typically 88% copper, 12% tin. Stainless steel is another. So stainless steel is mostly iron with small amounts of carbon and nickel in and some chromium. There are a lot of different types of stainless steel. Okay, this is one example here, but there's a whole bunch of combinations on stainless steel. There's a whole field out there of metallurgy that centers around stainless steel in order to have it resistant to certain chemicals or not resistant or just things like that. So stainless steel, we list one here, but there's a whole bunch of others. Another one, sterling silver. Sterling silver is only 92.5% silver. The other 7.5% is copper. So there's some other examples there, but those are ones that are a little more prevalent. And so this is an example of alloys where you take something that has one predominant metal to it and add other metals into it to give it some specific physical property that you're wanting. Okay, when we talk about alloys, there's different types of alloys that you can have. There's something called a substitutional alloy, and that's a case where the second element takes the place of a metal atom. So in this case, you have silver and gold, where you have them taking the place of the other. The next one is interstitial alloys. And so this is where you sneak a metal or some material in one of the gaps here. So you have the gaps based on that stacking, and you're able to get, in this case, they're putting carbon in that space, And then finally, the third one is heterogeneous alloys. And that's where, if you look at, and this is probably an electron microscope type of photo here, you see that it's not homogeneous. So in other words, we have Fe metal up here, we have Fe with carbon down here. It's not a uniform thing. It's more of like what I would call a doping of it, where you add it to the material. So this type of alloy, especially the doping one here, the heterogeneous alloys, that is a big area of study in the world of catalysis. So to make organic reactions go, a lot of times people add catalysts in order to speed up the reaction and make the reaction more efficient. A lot of those catalysts center around metals, and they're always fooling around to dope the metals with different things to optimize the catalyst. And then finally, there are intermetallic compounds. These are compounds, not mixtures. So in this case, when we were talking about these alloys, we've made kind of like a mixture, okay? This one, the difference is the intermetallic compounds, they're actually compounds that contain these different atoms. The other ones are, you've just kind of stuck it in there in one way or the other, one of the three ways we talked about. They have distinct properties, they have a definite composition because they are compounds, and they're very ordered. One negative to it is a lot of times they're more brittle. In my experience, are more along these alloys than the compounds, because the alloys people can control and put exactly what they want in. They can kind of vary the things that we talked about with some of those different combinations and stuff. Okay, finally, we've been talking about this electron C. Here's kind of a visual of it where you have the metal atoms with a little bit of positive charge. You have all these electrons with negative charge going around it. And the electrons have that electrostatic attraction to the cations. It's that opposite attracts thing that we talk about. And the other thing is the electrons aren't going to just sit on one atom. They are kind of just I think of it as kind of like a haze or something. They're kind of floating around in there. Electrical and thermal conductivity, the bendability, all that kind of stuff, it's explained by this model. Now, we're not going to get into the details of the model, but that's the general idea behind the metallic bonding. The other thing that is involved in this is explaining some of this through molecular orbitals. So remember last semester, we talked a little bit about molecular orbitals and molecular orbital theory. So I want to spend just a few moments talking about it with respect to the metals. And so we said we have this electron C model, and that leads to increased attractions for every electron added. And so what this means is that the melting points increase as you add electrons. And we see that. We go to the period 4 stuff and its melting point. We go to period 5, period 6, we see the melting point go up. We're adding those electrons, so what does that do? That means we have more interaction, right? We have those intermolecular forces are a little stronger. Since they're stronger, that means the melting point goes up. Now, these are all pretty good high melting points to begin with, but we see they go up as we have those additional electrons and go up from period 4 to period 5 to period 6 on the periodic table for those metals. So let's just take a moment to refresh our memories on molecular orbital theory. So remember, we said that atomic orbitals combine to make molecular orbitals that extend over the entire molecule. So last semester, we talked a lot about atomic orbitals, and then towards the end there, we went into molecular orbitals where we take those atomic orbitals and kind of combine them to form these molecular orbitals representing that whole molecule. Molecular orbitals can have 0, 1, or 2 electrons. The number of molecular orbitals equals the number of atomic orbitals that combine to form them. So if we have 1 atomic orbital from one atom and 1 for the other, then we'd have 2 molecular orbitals. When we add electrons to a bonding molecular orbital, remember we had bonding and anti-bonding. The bonding were lower energy than the anti-bonding. So we fill those bonding ones first. When we add molecular orbitals to that bonding, when we add electrons to that bonding molecular orbitals, it strengthens bonding. As you remember, when we add them to the anti-bonding molecular orbitals, it weakens the bonding. So if we're filling up all those bonding molecular orbitals, that's a real strong, stable situation. When we start adding more electrons, we get some instability because we're starting to fill the anti-bonding molecular orbitals. Okay, so here we have lithium as an example, and we'll kind of review that. As the number of atoms in a chain increases, the energy gap between the bonding and anti-bonding gets smaller and eventually disappears, where it becomes kind of a continuous band of energy. And that's what we have over here. So we started out on the left with lithium by itself. We have 1 electron, and we're talking about the valence electrons. Then 2 lithium atoms. We have 2 valence electrons. Those are in that bonding molecular orbital. We have 4. Now we have 4 molecular orbitals. We have 2 electrons here and 2 electrons in the second bonding one. When we go up to higher levels, in other words, more electrons involved from more things together, then we start getting this kind of continuous band of filling bonding and then having the anti-bonding. And in the metal situation, remember we said we have this sea of electrons. So when you get into that lattice, because I know you're thinking, what the heck is lithium 20 whatever? Well, remember it's that lattice that we have going on. And now all the electrons from the atoms in that lattice are kind of being shared amongst them. That's how you get to this kind of band of continuous molecular orbitals over here on the right. But it still means you have bonding and antibonding. And if we're filling up the bonding, it's going to be more stable than if we start going into the antibonding. Okay, so most metals, if you think back to the periodic table, most of them have d and p orbitals. And so what that means is they've got more of those valence electrons. And so that's all we're kind of saying here, is just going into it, showing that if you start having not just s orbitals, but d and maybe even p and d orbitals, then you start getting more of this continuum filled up, and you can start filling those bonding molecular orbitals. Okay, there's a little bit of homework associated with this part. And I would like to go through, I think it's just one of the problems. Let me see. 2 of the problems. Okay. Okay, so for 1235 rather, let's look at this. And we say iridium crystallizes in a face-centered cubic unit cell that has an edge length of 3.833 angstroms. So when I say edge length, what am I talking about? Anybody know? So when I have that unit cell, remember, and I would have from one dot to the other, one lattice point to the other, that's the edge length. Okay, so that's the first thing you need to know. Then they're asking us, and they're telling us that that's 3.833 angstroms. How long is an angstrom? What's the unit on angstrom? It's 10 to the minus 10th meters, right? So you need to remember that. And then it's saying calculate the atomic radius of an iridium atom. Well, for face-centered cubic, in the book, we know that A equals 4 times R times the square root of 2 divided by 2. That's a formula that we're given in the book. And so what we're going to do is we're going to use this formula to solve for R, because the radius is what we want. So 3.833 angstroms is our A value. R is what we're solving for. So we have 4R times square root of 2 over 2. So if we go ahead and do that math, we can divide each side by 4. That's our next step, 0.95825 equals R times the square root of 2 over 2. And then if we solve for R by dividing the square root of 2 divided by 2 into 0.95825, we get 1.355 angstroms as the radius. Okay, so the key there was understanding that with face-centered cubic cell, here's our relationship between edge length and radius. We were given the edge length, and then it was plugging it in. The other thing I'll say is, you have to take a square root there, you have to do some division, all that. Make sure you're comfortable with the keys on your calculator to do that calculation, all right? So then the second part is calculate the density of iridium metal. If we hear density, we should immediately think mass per volume, right? Mass is typically grams, volume is mils. What's another way of talking about mils is centimeters cubed. Since we're talking about shapes here, we're probably not going to talk about mils. We're probably going to talk about centimeters cubed, right? And so there's a couple things we can do is, one is if we added up how many atoms are in a face-centered cubic, we would see that there are 4. We talked about that a little earlier. If you don't remember, go back and review that. So we have 4 atoms there. So that tells us our first clue. So if we want to know how many atoms, how much that weighs, we can do that. 6.02 times 10 to the 23rd atoms there. Anybody tell me what that is? Where'd that number come from? Yeah, it's Avogadro's number, right? So Avogadro's number, which we learned early on, comes back here to tell us how many are in moles. We have the molecular weight here. And so now we've gotten our numerator into a mass value of grams. In the denominator, we want volume. Well, we know from up here that our edge length is 3.833 angstroms. So we need to change the angstroms into centimeters, right? So if we go, and this is 10 to the minus 10th meters is 1 angstrom. 1 meter is 10 to the second centimeters. And we convert this into centimeters. So that's our edge length. And if we want to find the volume of that, it's cubed, right? Length times width times height. So then we cube this number in the denominator, and now Our denominator is giving us the volume of the cell. So we have the weight of 4 atoms that will come out of the numerator, and the volume of cell will come out of the denominator. And that'll get us in grams per centimeter cubed as our final unit, which is what we want. Okay, does everyone see how we kind of walk through this? Any questions about that? Okay, I'd like to go through this one, but we're out of time for today. So we'll look at this next, well, it'll be next Tuesday when we get to this. Just to repeat once again, our quiz that we were going to have on Thursday has been moved to next Tuesday. Same material, same chapter 11 stuff, but it'll be then. This Thursday, and I'll send out put some things out on Canvas about this. There'll be a guest lecturer who's one of the candidates for a teaching position here, faculty position. And so I'll send information out on that, and I appreciate if you could dial into Zoom for that and give some feedback on the candidate and their presentation. All right, well, thank you.